When you see a massive mountain range and you just stop and wonder, how on earth did that get there? How does our planet build something so enormous, so solid, that it literally scrapes the sky? Well, today, we're going to peel back the Earth's crust and find out.
So, let's just start with the big question right up front. How do you build a mountain range? It sounds like a totally impossible job, right? But the Earth, well, it has a recipe it's been perfecting for billions of years. And here's the short version of that recipe. It's deceptively simple. First, you need immense, planetary-scale pressure. Then, use that pressure to literally bend and break the crust of the Earth itself. And finally, you just have to wait. For about, 500 million years. No big deal, right? Okay, let's dive into each of those steps. We're going to start with the raw power. What are these incredible, almost unimaginable forces that have enough strength to reshape entire continents and build mountains right from the ground up? Just take a look at this. This is incredible. These aren't waves of sand or water. Those are layers of solid rock. Rock that was once perfectly flat, now bent and buckled like a piece of paper. This is what happens when continents collide. It's a perfect visual of the power we're talking about.
So that really begs the question, doesn't it? What kind of force is so powerful that it can take something as solid, as brittle as rock, and just fold it? Well, the answer lies in one powerful idea.
And that idea has a name: orogenesis. It's the technical term for the whole shebang, the entire process of mountain building. And as you can see from the definition, it mainly happens through folding and faulting the Earth's crust, or, put more simply, bending it and breaking it. This is the engine of mountain creation.
So to understand how that engine actually works, we need to get into the fundamental physics, and it all boils down to two key concepts: stress and strain. This diagram right here, this is the key to understanding everything else. It lays out the three basic types of stress that are always at work on our planet: tension, which pulls things apart; compression, which squeezes them together; and shear, which makes them slide past each other. We're going to look at each one. So what's the difference between stress and strain? It's actually really simple. Stress is the force you apply, the squeeze in this case. Strain is how the rock reacts to that force. So here, the strain is the bend, or the fold. Stress is the action, strain is the result. Simple as that. All right, let's talk about compression. This is that squeezing stress. Just imagine two tectonic plates pushing against each other with incredible force. The crust gets caught in the middle, and it has nowhere to go but up. So it shortens, it thickens, and it buckles into those amazing folds we saw earlier. This is your classic mountain building force. The total opposite of that is tension. This is a pulling apart stress. When the crust gets stretched, it thins out and eventually cracks, creating these huge breaks that geologists call faults. This is how you get vast valleys and giant basins. And then you have shear stress. This isn't a head-on collision or a pulling apart. It's more of a side-to-side grinding motion, where tectonic plates scrape past each other. If you've ever heard of the San Andreas Fault in California, well, that is a massive, famous example of shear stress in action. Okay, so we've got our forces: compression, tension, and shear. Now let's see how these forces actually build the shapes we see in the world around us, from giant wrinkles in the Earth to these massive cracks. This diagram is basically the blueprint for a folded mountain range. When all that compressional stress squeezes the crust, it creates this really cool, predictable series of upfolds, which are called anticlines, and downfolds called synclines. And those are the two terms to know: anticline and syncline. An anticline is the arch, that upward A-shaped fold. A syncline is the trough, the downward U-shaped fold that sinks. An entire mountain range is really just a huge series of these anticlines and synclines, over and over again. And this slide is just brilliant because it connects the textbook diagram to reality. On the left, you see this simple drawing of a synclinal ridge. Now, look to the right. That is a real one in Western Maryland. You can literally trace that U-shaped fold of the rock layers with your eyes. It's geology coming to life right on the side of the highway. So we've seen the forces and the shapes they make. Now, let's zoom out, way, way out. We're going to look at how these exact processes, playing out over hundreds of millions of years, built an entire continent, Europe. This timeline really puts it all into perspective. We're looking at a 500 million year history of continents just crashing into each other, forming supercontinents, and then breaking apart again. And every single collision left behind a new mountain range. The geological story of modern Europe can really be broken down into three great mountain-building events, or orogenies, and each one left its own distinct mark on the landscape, creating the mountains we see today. First up, we have the Caledonian orogeny. This was an ancient one, kicking off almost 500 million years ago when the continents that would eventually become North America and Europe collided. The mountains this collision created are now the old, worn-down, beautiful highlands of Scotland and Scandinavia. Next on the scene was the Variscan orogeny. You could say this was the main event. This was the massive collision that mashed all the continents together to form the famous supercontinent Pangaea. It raised this huge mountain range across the center of that new landmass, and you can still find the remnants of it all across Central Europe. And finally, we have the Alpine orogeny. This is the new kid on the block starting a mere 65 million years ago. And the wildest part is, it's still happening right now. Africa is continuing its slow, steady push into Europe. This collision is what's actively building the sharp, young peaks of the Alps, and even the mighty Himalayas farther east. They're still growing. The Alps are rising about 1 millimeter a year, which is roughly the same speed your fingernails grow. How crazy is that?
So, if there's one thing you take away from all this, let it be this. The ground beneath our feet is not static. Mountains aren't permanent fixtures at all. They are the dynamic expression of a planet that is constantly in motion, folding, breaking, and rebuilding itself over absolutely epic timescales.
And that leaves us with a pretty fascinating final thought. We know the Alps are still rising, we know the continents are still moving, so what do you think the map of our world will look like in another 50 million years? What new mountains will have been born?